Hello students. So in moving charges and magnetism, also it is a part of electrodynamics. We already discussed about two important concepts. First one is Oersted experiment, which is the basis for the electrodynamics, the development of the branch of electrodynamics, from which it has been found out that electricity and magnetism are two sides of same coin, they are not different. So after that, in the same year, Biot and Savart, they arrived with a mathematical equation for finding out the magnetic field induction or magnetic induction due to a current carrying element that is IDL element, which is a vector, and it is similar to the charge in electrostatics. Okay. Now, so this Biot-Savart's law is universal, means whatever the type of current distribution may be, whatever the type of conductor may be, whatever the shape of conductor may be, to find the magnetic induction at a point, we can use universally that is Biot and Savart's law, no doubt in that. So when we recall about electrostatics, we know there are two laws in electrostatics. One is Coulomb's law. One is the Coulomb's law. So we have Coulomb's law, and another one is Gauss law. One more is Gauss law. So these are two laws in electrostatics. So here Coulomb's law is universal for electrostatics. When the charges are at rest, we want to find what is the electric field or electric force, we are going to use the Coulomb's law. Okay. So Coulomb's law is universal for electrostatics. But however, well, there is some sort of symmetry in the charge distribution. So whatever the charge distribution, irrespective of the charge distribution, we can use Coulomb's law, no doubt in that, it is universal. But however, suppose the charge distribution is having some sort of symmetry. We have seen there are three types of symmetry in the charge distribution. What is the three types? Planar symmetry, we have planar symmetry there. So planar symmetry. Next one is spherical symmetry, and another one is we have cylindrical symmetry. So if the charge distribution is having some sort of symmetry, that is three types, then it becomes very, very convenient and time saving to calculate the electric field due to the symmetric charge distribution. In that case, Gauss law we are using. But Gauss law is not independent. Gauss law can be derived from Coulomb's law. So Gauss law is not a separate law. We can derive that Gauss law from the Coulomb's law. Same comparison now. Same comparison. Here in electrodynamics, we have, see here, this is analogous to, we can say now, Biot-Savart's law. Biot-Savart law. Analogous to Biot-Savart's law. That means what? In electrodynamics, when we want to find the magnetic induction at a point, then we are going to use Biot-Savart's law, irrespective of the distribution of the current carrying element or current carrying conductors. Whatever the shape of current carrying conductor, whether it may be symmetric, non-symmetric, whatever it may be, complex, complicated, anything, we can use Biot-Savart's law to find the magnetic induction or the magnetic field induction at a point due to the current carrying conductor. Okay. But however, if there is some sort of symmetry in the current carrying element or current carrying conductor, If there is some symmetry, then it will become very, very convenient to use this, what do we call, the Amperes law. So, if the current carrying conductor or the element or the current carrying what do you call current element is having some sort of symmetry, then it is very, very convenient to use Amperes law, just like Gauss law. Just like Gauss law, we can use this Amperes law. Okay, but there should be some sort of symmetry. But we know practically when we take any current carrying conductors, they are all symmetric only. Example, when you take our electrical wire, you see the transmission line, or you take our domestic wire, they are all cylindrical. So, when we want to find the magnetic induction at a point due to a symmetric current carrying element, then it is very, very convenient to use Amperes law. So, now we want to know what is Amperes law, what is the statement of Amperes law, and what are the important points when we want to apply Amperes law, or what is the important characters or points that you have to keep in mind, and after that how to apply this Amperes law for a solid cylindrical conductor and a hollow cylindrical conductors. So, both solid cylindrical conductor, hollow cylindrical conductor, we are going to use the Amperes law. Okay. So, now let us see what is this Amperes law or Amperes law statement. First we want to know what is that Amperes law statement. So, Amperes law statement, we want to know first what is the Amperes law statement here. Okay. So, now let us see what is the statement of the Amperes law. So, first of all, here when we want to apply Amperes law, means we want to know the statement of Amperes law, we are going to take some imaginary loop, maybe real, maybe imaginary. Most of the case it is imaginary loop, that is closed surface, imaginary loop that encloses the current carrying conductors, right. We know when a conductor is carrying current, means here the current can be coming out of the plane or going into the plane. Like magnetic field, if the current is coming out of the plane, means example board is a plane. Suppose when a current is coming, a conductor is there carrying the current, that current is flowing upwards, that is coming out of the board, and it is going down, that means current is going into the plane. So, now suppose for example there are two conductors here, say there are two conductors minimum, for example I am taking two conductors. So, there are two conductors carrying current. So, this is one conductor, and say this is another conductor. Two conductors, any number we can take, but for example to know the statement I am taking only two conductors now. In this now see here one conductor is carrying current into the plane. It is carrying current into the plane. Okay, into the plane. Means it is going into the board. Next, another one, it is coming out of the plane. Another conductor is carrying current out of the plane. So, second one is out of the plane. So, these two conductors, right. This is another conductor. Now, we want to find the magnetic induction at a point in the space due to these two current carrying conductors. Then what we are going to do is, we are going to imagine that these two current carrying conductors are enclosed by a closed surface, an arbitrary closed surface. Arbitrary means it is our choice. According to our convenience, we are going to choose the shape of the loop. We are going to take the shape of the loop. Okay, so we are going to take the shape, arbitrary I am taking like this now. So this is the shape of the loop. As it is, I feel convenient, I am taking this is the shape of the loop. Okay, so this is the shape of the loop here. So shape of the loop, right, that is my shape of the loop. This arbitrary loop which we have taken according to our convenience, we call it as Amperian loop. This is known as Amperian loop. So that loop is called Amperian loop. So this is the Amperian loop. Okay, Amperian loop, right? Amperian loop. So Amperian loop. Amperian loop. This is called the Amperian loop. Okay. So that is your choice. According to your convenience, you are going to, whatever the shape you feel comfortable, that you are going to take. Because the magnetic induction, due to this current carrying conductor enclosed by the loop, does not depend upon the size of the loop, it does not depend upon the shape of the loop. That's why whatever your choice, whatever you feel convenient, that you can choose. That is called Amperian loop. That is known as the Amperian loop. Now, according to according to Amperes law, if we are going to take the line integral means what? We are going to perform integration around this loop. Then we call it as line integral. Means what? First we will take one small element. We are going to take one small element on the surface of the loop. Small element we are going to take on the surface. So we take one small element here on the loop. Okay. So once we take that element, then what we will do is we are going to find what is the magnetic induction due to this loop. Then after that we are going to integrate around this closed loop. That is called line integral. And that line integral is B dot dl. So B dot dl. B vector we know, no? Magnetic induction is a vector. Dot dl. That is this one. This element is of length dl. And we know already the direction of this length element. Direction of this length element is the tangent drawn at this point. So B dot dl, cyclic surface integral means we are performing the integration around this closed surface. When we are going to perform the integration around this closed loop, then we call it as the line integral of B dot dl. That is equal to mu naught times the current enclosed by the loop. Mu naught times the current enclosed by the loop. Well, the current elements are either in air or in vacuum. Then according to Amperes law, the line integral B dot dl is equal to mu naught times the current enclosed by the Amperian loop. That is the statement of the Amperes law. So here Amperes law, this will write more clearly here. So this one now, current enclosed by the Ampereal loop. That is the Ampere statement, Ampere law. That is, we call it as Ampere's law. So this is our Ampere law. So Ampere law. Right. The line integral of B dot dl is equal to mu naught times the current enclosed by the Ampereal loop. That is our Ampere's law. Right. Here, when we want to find this, when we want to use Ampere's law, important point is here the direction of the magnetic field is immaterial for us. That is not very important here. So when we perform integration, automatically the magnetic field is we are going to get the result. That means what? Suppose initially this is the direction of our dl, no? So now suppose here this dl is making an angle, say theta, with the direction of magnetic induction. So this is the direction of, say, magnetic induction, that is the B here, and this element is making an angle theta. Means our line element is making an angle theta with the magnetic induction, that is magnetic field induction. That means what? This direction is not important for us. It is arbitrary here, because when we perform the integration, depending upon how we are going to integrate that line integral, the direction is going to come out automatically. Suppose we assume that it is radial outward. Suppose if it is true, our result is also going to be true, that will come positive. Suppose it is into the radially inside, let us say, then it will come negative. So when we choose one direction, if our direction is correct, when we perform the integration, line integration on the surface, if the result is positive, our direction is correct. If result is negative, direction is opposite. That's why here we need not bother about the direction of this magnetic field induction. That is not very important here. Okay. So that is the thing here. So what we are going to do is, when a current carrying conductor is given, we are going to choose one Amperian loop. Then we are going to take one element, we will calculate what is the magnetic induction, then we are going to perform integration around that loop under proper limits. Then we are going to get the value of this B. Okay, that is the way to choose this one. Now, how to choose which current is positive, which current is negative? Which current is positive, which current is negative? For that, again we are going to use the right hand palm rule, the stretched right hand palm rule. That is, what we are going to do is, we are going to stretch our fingers, that is the palm, and we are going to imagine that we are holding this loop in our palm. We are holding this loop in our palm. See this. We are holding the loop in our palm, and when we hold this in our palm, these fingers must be in the direction of our line element, like this. See, this is the tangent we have taken, no? Anti-clockwise we are performing now. The integration we are performing anti-clockwise. So we imagine that we are holding this in our palm anti-clockwise direction. Now, if the current, if the thumb will indicate the direction of that current. If the thumb is coming towards us, then the current is coming out of the plane. If the thumb is going into the plane, then current is going into the plane. That is simple. That is simple. Once again you listen, when we are going to perform the integration, to know the direction of current, we are going to stretch our palm, fingers, and fingers are going to be kept in the direction of integration. Here we are going to perform integration in the anti-clockwise direction. Therefore, I stretch my palm in the anti-clockwise direction. If the current is coming, if this thumb will indicate the direction of current. If the thumb is coming towards us, the current is coming out of the plane. If the thumb is going into the plane, then current is going into the plane. That is very simple. So generally out of plane we take positive, into the plane we take negative. So net means what? What is meaning of net? Total. Means when the current is going into the plane, that is negative. Suppose we are taking negative and the current coming out of the plane, we take positive. Then what is the net? Suppose this is 1 ampere, this is 2 ampere. For example, this is 1 ampere, this current is 1 ampere and this current is 2 ampere. Right? Then what is I enclosed? What is I enclosed now? I enclosed is equal to, this is our I1, this is our I2, let us say. Then what I will write? That is equal to I2 minus I1. I2 minus I1, that is 2 ampere is out of the plane minus 1 ampere into the plane. Therefore, I enclosed equal to 1 ampere. I enclosed equal to 1 ampere. Then mu naught into 1, that is mu naught. Then what I will do is, most of the cases B will be uniform magnetic field, because it is a symmetry element. So we take B outside. So what we will do is, B is constant here. Then we take B outside. Then integral of, line integral of dl. Means, what is line integral of dl? This total length of Amperean loop. The total length of the Amperean loop. So that is the way we are going to perform this line integration. Once we know the line integration, we can find out the value of B for this Amperean loop. So that is the method to find the magnetic induction due to a current carrying conductor or group of current carrying conductors. Right? So that is the Ampere's law statement, and how to apply that Ampere's law. Now here, related to Ampere's law, we have to keep in mind some very, very important points. Right? Some important points are there when we are using this Ampere's law. First point. So important points. Here, important points that we have to keep in mind. So important points here related to Ampere's law. Number one, first point. Here, when we are using Ampere's law, number one, shape of Ampere loop, size of Ampere loop, and the position of current carrying conductor is not important. So number one point, shape of Amperean loop, and position of current carrying conductors, current carrying conductor is not important. This very, very important point is not important. It does not affect B value. Whatever the shape may be. Whether I told you, according to convenience, you can take this is your shape, or you can take this is your shape, or this is your shape, whatever it may be. That is not important here. B value do not change. Not only that, position of current carrying conductors. So position may be here, or one position may be here, or position may be here. That is not important. Here, this may be the position, this may be the position, this may be the position. That does not affect B value. So that is first important point you have to keep in mind for theory question also. Next, second one, Second important point here, this is the major point, very important point. Second important point is generally this Ampere law is useful for steady currents, that is very important. So, second one, steady currents, used for steady currents, used for steady currents, used for steady currents, not unsteady currents. Variable currents, it won't be useful. It should be a steady current, then only it can be used. So, Ampere's law can be used only for steady currents. Next, third one, this, as I told you in the beginning itself, Ampere's law is not independent law, it can be derived from Biot-Savart's law. That point also you have to keep in mind for theory question. Ampere's law is not independent, it can be derived from Biot-Savart's law. That is also important here. Okay. So, that points you have to keep in mind, three important points. Number one, shape and position of the conductor in the Amperean loop, and number two, used for steady current, and it is not independent, it can be derived from Biot-Savart's law. Right. So, that is about the Ampere's law. Right. Now, we want to use, means we want to apply this Ampere's law to find the magnetic field or magnetic induction inside a conductor, outside the conductor. Because by using our Biot-Savart's law, we can do it. But when symmetry is there, this will become very, very simple. No complex mathematics is required. So, that is now we are finding out magnetic field. So, magnetic field outside a conductor, magnetic induction, outside a conductor, outside conductor. That is, here we are taking a solid cylinder, conductor is a solid cylinder, our wire. If you take our electrical wires, they are all solid cylinders, no? You take any you can open your electrical wire, you can see transmission line, they are all cylinders, cylindrical shape, isn't it? So, suppose when we see that this one, for example, this is also like approximately cylinder. So, when you see the cylinder and cut the conductor, see how it will be? You just see this one. You can see like this, no? Means what? It is just like one circle. So, when you take that, it is just like a circle. So, here, this is just like a circle here, because it is a circular in section. So, circular in section. So, conductor is circular in section. Suppose its radius is r. The radius is r. The center and radius is r. R is the radius of the conductor. R is the radius of the conductor. Okay. So, R is radius of the conductor. Okay. Now, what we want to find is, this conductor is carrying a current I and it is uniformly distributed. See, this is our conductor, no? Like a cylinder. This is the conductor. Okay. This is the conductor. This is our section, circular section. Right? Now, this is the radius, this is the axis of the conductor, axis of the cylinder, and radius equal to capital R. We have taken radius equal to capital R. Okay. So, this is radius, and it is carrying a current, and current is uniformly distributed. So, it is carrying a current I upward, let us say it is carrying current I upwards. I, not I naught, is carrying current I. So carrying current I. Now we want to find what is the magnetic induction at a point, a distance smaller from the center of the conductor, that is from the axis of the conductor. Axis of the conductor. From the axis, we want to find what is the magnetic induction due to this current carrying conductor outside at a distance r. Outside at a distance r. See this. Now I want to find what is the magnetic induction at this point, say P. At this point, that is P. That point is P point. So right now I want at this point. Now what is my Amperean loop? What is my convenient Amperean loop? It is a circle. So this is R. Now what I will do? By taking R as radius and the point on the axis, suppose point on the axis O, let us say, O as center, we are going to draw a circle. We are going to draw a circle now. Right. So this is our Amperean loop. This is our Amperean loop. Amperean loop. Okay. Now, so what is this Amperean loop? A circle of radius r. A circle of radius r. Now what is the current enclosed by this Amperean loop? What is the current? Total current enclosed or not? I totally it is enclosed by the Amperean loop. Therefore, I enclosed is equal to I. I enclosed is equal to I. Because total current is enclosed. Total current is enclosed. Therefore, I enclosed equal to I. Then what we have to do now? Here. So we are going to now applying this Ampere's law. So surface integral of B dot dl equal to mu naught into I enclosed. Mu naught into I enclosed. I enclosed how much? I. Total current is enclosed here. Therefore, mu naught into I. Mu naught into I. And here B is a constant, isn't it? B is a constant at this point because current is steady. Therefore, B we can take outside. B into surface integral of dl equal to mu naught into I. What is the length of this circle? This is our Amperean loop, no? So what is the length of this Amperean loop? That is circumference of the circle. Therefore, this we can write surface integral of dl, line integral of dl equal to B into 2 pi r. That is equal to mu naught into I. And here you may have doubt. Sir, B dot dl is B dl cos theta. How have you taken cos theta is 1? How do you decide that cos theta is 1? Means how do you say theta equal to 0? For that, see this. When I take, where is my element? This is my element, no? This is the direction of my element, dl. And what will be the direction of the magnetic field? Magnetic field also will be in the same plane. That means the magnetic field also in the same plane. That is dl and B are parallel to each other. So theta is how much? See the point here. Magnetic field is in the plane of the board. dl is also in the plane of the board. That means dl and B, they are parallel to each other. Means theta is equal to 0. When theta equal to 0, cos 0 equal to 1. Therefore, B dot dl, we can take it as B dl, and B is a constant here. Therefore, surface line integral of dl is equal to length of this element, Amperean loop, that is circumference of the circle. Therefore, it will become B into 2 pi r, that is equal to mu naught into I. So, what is B value now? Finally, what is our B value? B is equal to mu naught I upon 2 pi r. Same result we got in Biot-Savart's law. By using Biot-Savart's law, we got the same result. Same result we got here, but very simple. Not much integration, nothing. Within a few seconds, I can get the result. That is the advantage of this Amperes law. So, for a current carrying conductor of infinity length, long conductor, carrying a uniformly distributed current I, the field magnetic induction at a point outside is mu naught I by 2 pi r. That means here what is the condition? The condition is here small r greater than capital R. Means the point is outside the conductor. The point is outside the conductor. Now, let us take point inside the conductor. So, field at a point inside the conductor. Field at a point inside the conductor. So, this is outside we have taken now. Now, we got the same result. So, outside we got same result now. Now, what we want? Field inside. Field inside the conductor. Field inside conductor. Inside conductor. So that means what? Our small r less than capital R. Small r is less than capital R, right? So now again let us see our section of the conductor. So we are taking first the section of the conductor. So we take the section of conductor here. So this is the section of the cross section, means we are seeing from the section cut view. This we can say cut view now. So what we want here? We want inside a point inside. So for that, just see this. See that point inside. So when we take the point inside here, so this is the point inside now. See the conductor, this is our conductor having a radius r. So this is the axis of the conductor. So this is the axis, right? Center point, line passing through the center. Okay, this is our circular section. So this is our circular section, right? So this is our conductor of long conductor. Now what we want? We want the magnetic field at a point inside. This is the point. This is our point P. Right. Now from the axis means O point, this distance is r. Radius is r, we can say. Radial distance is r. Now what is our Amperian loop? What is this conductor? Cylindrical? No. That is circular section. Therefore, we are going to use here a circular loop. We are going to use the circular loop. So, circular, we will draw a circle. We are drawing a circle here. This is our Amperian loop. This is our Amperian loop. So, this is the Amperian loop. So, Amperian loop, which is a circle, right? So, theta is how much? Theta equal to again 0, because this is our element, this is the direction of the element, tangent, and field is also in the same plane. Field is also in the same plane, B is also in the same plane. Therefore, dl and b are parallel to each other, both vectors are parallel, that means theta equal to 0. Therefore, what we have here, now write the line integral of b dot dl is equal to mu naught into I enclosed. Mu naught into I enclosed. Here we know B is a constant because current is steady and uniformly distributed. What is the total current by the conductor? I. Complete conductor is carrying I. That is very important here. Means in this case all the current is not enclosed by our Amperean loop. That we have to calculate. First that we have to calculate. Okay. For that B is a constant here. Then what we have? B we can take outside into integral of line integral of dl. That is how much? dl is how much? It is circumference of the circle and radius is smaller. Therefore, B into 2 pi r. B into 2 pi r. That is our B dot dl. Line integral of B dot dl. Now what I want? I want I enclosed. What is the current enclosed by this Amperean loop? For that, we are going to use the concept of current density. First, we will calculate current density. So, what is the current density here? Current per unit area. Current per unit area, isn't it? So, what is the current per unit area? What is total current? So, J is equal to magnitude of J is equal to total current divided by total area of cross section through which current is passing, that is pi into capital R square. That is the total area, no? Total area of cross section, because we know this is the radius capital R, that is capital R. Therefore, J equal to I by pi r square. So, what is the current enclosed now? J into area of our Amperean loop, isn't it? Therefore, that is equal to, we can write I upon pi r square into pi into small r square. Because the radius of our circle is smaller. The radius of circle is smaller. Therefore, our area is pi r square. Right? This is like cost of one apple into number of apples. Similar, same thing. So, pi gets cancelled now. Therefore, what is our current enclosed? This is I enclosed. I enclosed equal to r square small r square by capital R square into I. Into I. That is our I enclosed. I enclosed. That is the enclosed current. Enclosed current. This is our enclosed current. Once we know I enclosed, now we can B into 2 pi r. B into 2 pi r. So, B into 2 pi r, B into 2 pi r, B into 2 pi r is equal to mu naught into small r square by capital R square into I. Into I. So, R square gets cancelled. So, what is our field magnetic induction? At a point inside, B is equal to mu naught I by 2 pi capital R square into small r. Isn't it? So, inside the conductor, mu naught I by 2 pi capital R square into small r. This is a magnetic induction at a point inside the cylindrical conductor. Mu naught I by 2 pi capital R square into r. means what? Inside the conductor, B is directly proportional to R. Means inside conductor, the induction, magnetic induction changes linearly. But outside, it is going to change inversely as distance. Inversely as distance. That is, rectangular hyperbolically it changes. Rectangular hyperbolically it changes. And at the surface, it is maximum. At the surface, it will be maximum. Because at surface, small r equal to what? Capital R. So, capital R square gets cancelled, mu naught I by 2 pi r. So, 3 values we have now. 3 values here. That is very important here for us. All the results now. So, 3 values. We have all the 3 values now. Right. First, so for solid cylindrical conductor having a uniformly distributed current. Uniformly distributed current. I will write all the results now. For solid cylinder, right. For solid cylinder, we have first 1 small r greater than capital R. Small r greater than capital R. Okay. So, small r here greater than capital R. Right. Small r greater than capital R. What we will get? Outside B is equal to, we have mu naught I divided by 2 pi r. This is our first result. Next, second result, small r. So, small r is equal to capital R, that is surface. So, small r equal to capital R. When we take small r equal to capital R, at surface, B at surface equal to mu naught I upon 2 pi capital R. This is maximum. Maximum field induction. Next, third one, small r less than capital R, means inside the conductor, at the surface of conductor, at surface, this is outside, this is outside, this is inside. So, inside we have B is equal to, we can write mu naught I divided by 2 pi r square into small r. So, graph is very important. Quite often they are asking the graph. They are asking graph now. See, outside B is proportion 1 by r. Br is a constant. Next, at surface maximum. And inside directly proportion small r, because capital R is a constant. Radius of conductor is a constant. Therefore, our graph will be like this now. So graph will be, if we are going to plot a graph, the graph is like this. So this will be the graph now. We are plotting the graph. So here center is our reference. This is our reference now. Now this is our y-axis, along which we are going to take the magnetic induction, and x-axis we are going to take the distance. We are going to take the distance. So here this is B and this is R. So up to surface, we will take first up to surface. This is up to surface. Right. So up to surface, what do we have? Linearly changes. So up to surface, linear, it changes linearly. Right. It changes linearly. Okay. So B is proportional to R. B is proportional to R. Then outside, B inversely proportional to R. So outside it will be like this. So B proportional to 1 by R. Here B proportional to 1 by R. And this is maximum. This value is maximum at the surface, and that maximum value is equal to how much? So maximum value mu naught I by mu naught I upon 2 pi capital R. So this is the graph for a solid cylinder conducting current having uniformly distributed current. It's very important. Uniformly distributed current, this is the graph which is very, very common in the exam. Both MSET, JEE Main, other exams also, this is very, very common. So next we have a hollow cylinder that we will see next coming class. Then we will do problems based on this Amperes law, right?